All right, welcome everyone to this week's Autonomy Talks. This week is a great pleasure to have with us Professor Carlo Pinciroli, who is an associate professor at the Worcester Polytechnic Institute. And there he leads the NEST lab. And today he will tell us more about the lab. So his research interests include multi-robot systems, swarm intelligence, and software engineering. And as we were chit-chatting before, he contributed in various ways to this literature, and I found his work extremely interesting. And as you've seen also from the bio, is won a number of awards for the great work the lab has produced. And specifically, we were connected through the Amazon research has done on this very interesting motion planning problems. Today, Carlo is going to talk about 3 lessons on heterogeneity in robot swarms. This is a very interesting topic, and I feel it's not treated enough in the literature, and I'm very happy to hear more about it. Carlo said this will be an informal session, or he really is happy to have interactions and have questions. So please use the chat or directly raise your hand, and I will monitor that. And without further ado, join me in welcoming Carlo. The stage is yours.
Thank you so much for the invitation. This is really cool to be here. All right, so as I said, the talk is very informal, and I'm going to essentially jump right into it. So why did I pick this topic? First of all, is because robot swarms very often are assumed to be homogeneous, so all the robots being exactly identical. And there's very interesting things that happen when you think about heterogeneity in robot swarms. And so I just wanted to distill 3 lessons that I personally learned really through the work of my lab, and 1 bonus lesson at the end that is kind of like hopefully a call for action, let's say. I don't want to really give you an introduction. Let me just jump into the first lesson on heterogeneity, because honestly, that's where my introduction is. So the motivation to look into heterogeneity was from a project that was funded by NASA and just literally finished last week. So we went to JPL and presented our things. And that project, among the many things that we learned, just showed us just how much heterogeneity can be a challenge. So the project was about having robots on the moon collecting resources, and you can imagine resources could be helium-3, some funny regolith, or even just looking for ice water in some form. The point is, we have robots that are supposed to do tasks of different kinds, and we are on a planet in this case, or maybe the moon. Now, this cannot be the moon. This picture cannot be the moon because there's no atmosphere on the moon, so we cannot have a drone there. So let's say that this is Mars. But the point anyway is that when we deploy robots that are supposed to execute tasks of this kind, it is let's say, not realistic to think that we're going to just send robots that can do literally everything. Especially as we want to scale up operations, we're going to have to accept that robots will need to be specialized. And this brings us to the concept of having robots with specific skills. And so here you see in this picture, robots that can fly, robots that can walk on uneven terrain and also can collect some interesting resource, other robots that can move with wheels, and also have the ability to collect resources. And then you have robots dedicated to just having resources dumped into them and then, for example, bring them to a central location. The entire point here is to say that if we have robots that are specialized, then the tasks will also need to be specified as needing certain skills to be available. So, for example, if it's a collection task, you need to be able to dig. But then, for example, the nature of the location of where you dig might call for a certain type of digging, for a certain type of drill, for example, as opposed to a shovel. So the idea is that we want to have several tasks, and we want the robots to follow this kind of progression in which the robots initially have scouts, for example, that look for interesting places where we want to deploy the robots and execute tasks. And then, for example, this scouting can be done by drones. And then once this is done by drones, the drones, for example, come back or talk to the central location, the headquarters, and start recruiting robots. And so the robots dynamically form this these teams that we call coalitions, depending on what skills are needed, in which location, at which time, according to what the task needs. So this is a problem of simultaneous scheduling of tasks, so in which order we should do the tasks, but also coalition formation, so which robots we need for any specific task. So that's essentially the very first definition of heterogeneity we're going to see today. Having robots that cannot just do everything, but they're specialized, and so they need to form groups. Here I have an example, just, because I don't want to be too boring. So I have a video that we showed, and this was a video that we did even before, this NASA project was a technology demo for MathWorks. So in this case, we have robots that are white or black and white. And so that means that they have either one skill or two skills, either the white skill or the black skill or both. And then the tasks have either a requirement for both, or they have a requirement for only one. And so as you can see, there are robots that need to team up dynamically in order to complete all of the tasks. And this is essentially what we're looking at. Okay, this is the result that we're trying to achieve. This specific thing is done with a centralized algorithm, but later I will present also the decentralized algorithm. So anyway, this is the result we would like to obtain. So what is difficult about this problem? Why do we care at all about this problem? First of all, one of the things that is really interesting about our version of this problem is that we assume that task execution only starts when all the robots are present. And this is because we want coalitions to really, really be important. So we don't want just robots to arrive whenever they want, but we want to consider coalitions because this also creates interesting variants. For example, one of the things that can happen is that we have cross-scheduled dependencies across tasks. So if one robot, for some reason, is late, and it's needed for a certain task, well, it's going to make everybody else late as well. This is because the coalition cannot start working unless everybody is there. So one problem that we get is that as the number of tasks increase, the computation time also increases, and it increases exponentially. And this is because it's a combinatorial problem that essentially is NP hard. And so this is one of those problems that you cannot just brute force and hope that it's going to work. So typically, your reaction to that is to say, bye-bye optimality. So we are going to accept that we have optimality for small instances of the problems, and we're going to show you an algorithm that achieves that. But if we want to solve it at scale, we're going to have to use other ideas. And the second problem that arises is that if we just use local search, so we say, okay, bye-bye optimality, but we can just use local search, we are going to have deadlocks. And the reason why we have deadlocks is that there might be robots that distribute in the environment and they wait for each other. So for example, I need a shovel and I am a robot that basically is a truck, but then the shovel robot is waiting for a truck. And so there is this mutual dependency. And so one of the issues that we have is that if we're not careful, we are going to have to say bye-bye to also completeness. So we might not find solutions. So how do we find optimal solutions in this case? One of the ways in which we can do it is to devise algorithms that are based on mixed integer linear programming. Now, in the spirit of keeping everything very high level and formal, I'm not going into the mathematics. It's very grueling. I mean, it's MILP, so it's never fun to go through all of the equations. I'm very happy to do that, though. It is just to say that because mixed integer linear programs in this case, in this specific case, can be expressed in a convex way, we have actually the guarantee that the solution will be optimal. But one of the things that we very early on discovered is that only small problem instances can be solved in times that we consider reasonable, which is usually hours. So this algorithm was there just because we needed a baseline, and that's what we did. So more interesting is how do you find solutions that, okay, are not optimal, but you do it very quickly. So in the same paper in which we introduced the MILP algorithm to this, we initially thought about a very, very simple idea. So one could be that initially we pick the task with the largest skill requirement, and this was really inspired by constraint optimization, heuristics in constraint optimization. So we said, let's get the task with the largest skill requirement, and then after that, we're going to pick the robot that can fulfill the most skills within that task, and then if we have ties, we pick the closest robot to the task, and then we keep adding more and more robots to the task that we picked at the moment, according to how the contribution that the robots can give. And then once a task has completely been filled, we go to the next task, again with the idea that we pick the next task with the largest skill requirement. And we keep going in an iterative way, and if there are unassigned tasks, we go to one. Again, it's a very, very crude approximation. There's a number of interesting kinks to it, but the essential idea is this one. It's very, very crude. The nice thing about it is that it actually isn't that bad. So it's not probably the smartest idea you can think about, but it is, pretty effective. So the greedy solution is, in terms of cost, in the worst case, twice as bad as the optimal cost, which is, given the simplicity of the solution, it's not so bad. But the interesting part is that the computation time is a millionth of MILP. So that's nice because, in principle, one could run this heuristic algorithm and then, for example, hot start MILP in a solution that is not so bad. So you could employ combinations of this kind. But anyway, so the point is that even, a heuristic that is so simple gives you something already to start to work with. And the nice thing is that it scales nicely. So we can, for example, go to number of tasks in the order of 1024 and still get problems being solved in about 50 seconds. And so it's a really good, let's say, starting point to create a baseline. So basically now we have a very slow but optimal algorithm and a very fast, kind of crude, simple algorithm that gives us results very quickly. So what I'm trying to get to here is to fill the gap between these two extremes. And so one of the things that we thought about was to take advantage of an algorithm, that is actually a family of algorithms. It's a meta-heuristic called ant colony optimization. Now, the interesting part about ant colony optimization, I don't know if you know how it works, is that it uses the concept of an ant to build paths in a graph. And so we have this ant that starts in a random location of the graph, and then randomly chooses the next location to visit, and then the next location to visit, until basically the path is completely filled. And when the path is completely filled, depending on the quality of that path, we leave some pheromone along the path. Now, ACO is nice because it's essentially state-of-the-art in many TSP-like problems, real-world problems, even routing problems in networks, which is surprising to even think about. So it's the Bellman-Ford algorithm is awesome, but there's ACO-based algorithms that are challenging that in terms of quality. Now, what is interesting, though, is that in this case, we cannot just use an ant easily, because here we're talking about forming coalitions of robots. And so we explored two ideas. One idea is, we call it TACO because we liked the name. We called it territorial ACO. I have no idea why territorial. We really liked TACO, and so we decided that was the name, but we didn't have a good T word for that. But whatever, so territorial ACO it is. The idea in that case is that one ant is a robot, okay? And the thing is that we just basically allow each individual robot to form a path probabilistically. So it's essentially a little bit like Monte Carlo search. And then we allow the deadlocks to form sometimes, deadlocks again, with robots mutually waiting for each other but not being able to form a full coalition. And then in that case, what we do is that if we discover that there's deadlocks, we have a mechanism to say, well, certain ends can just be released from a piece of their path so that they can join other tasks. And so in that case, we solve the deadlocks. It's a form, if you want, of backtracking search applied to this Monte Carlo search. So this is one idea. So an ant is a robot. The second idea we call the swarm ant system, so SAS, is that we consider an ant actually the full swarm of robots. And so it's like a little bit like moving like a circus, right? And so in this place, we're gonna need, the elephants, and we're gonna need, the acrobats. And so, okay, we're going to deploy the elephants and the acrobats here, and the rest is going to stay inside the circus. And so basically, task by task, we release the robots that we need according to what the task requires. What's nice about this is that you cannot have deadlocks in a system of this kind, because essentially you are treating this problem of coalition formation like it is a normal TSP, or anyway, a normal task allocation problem in which you don't have coalition formation. And in particular, one of the things we were hoping to find is that by moving all of our swarm with all the tasks as a circus, we could discover more efficiently solutions that are not possible with TACO. And so we compared the two together with MILP. And so in this graph, what we want is to really be in the bottom left corner, because we start from 1 because it's a ratio. It is a ratio of two possible ways in which we can formulate the problem. We can formulate the problem as the total cost of executing a plan. So basically how long it takes to execute a plan in total. And then the max cost, it is the sorry. It is the longest a specific robot will take to finish its part of the plan. And so these are the two metrics that we consider. And with both of them, we would like to be in the bottom left corner, which is 1.0, because it's the ratio between what MILP tells us is optimal and sorry, it is the ratio between what this algorithm tell us they found and the solution, the MILP given solution. So this is why when you are optimal, you basically get to 1, and when you are suboptimal, you're greater than 1, because basically this is a cost. And what you can see is that what is nice about TACO and SAS is that they both tend to crowd very much the corner in the bottom left, which is there's an interesting thing though. TACO tends to be a little worse when we consider max cost, and SAS tends to be a little worse when we consider total cost. I see someone in the chat. Oh,
yes,
someone is asking about slides. Are the slides visible?
Yes.
Oh, okay, all right.
I don't know what Alice is referring to.
All right. I am on slide 10, just to make sure that you can see the same slide.
Yeah. We can.
All right,
yeah,
perfect.
of course. I mean, I would have.
No, just to make sure.
Would have blocked you. No. I'm not sure, Alice. But please follow up on the chat. But yes,
Sure,
slides are supposed to be presented.
Fair enough.
Nice.
Okay. Yeah, no problem. Absolutely. So the other thing is, we want to compare time, okay? And what we find is that SAS and TACO are significantly faster than MILP when we compare, for increasing number of tasks, which is nice. So now we have an algorithm that basically is, pretty good in terms of optimality, definitely better than the crude heuristic algorithm that we considered, and it is also faster than MILP. But obviously, we're not in the order of milliseconds like we were in heuristic. And so we have now basically 3 or 4 algorithms that can place us along the two axes of like computation time and expected quality. If we do a comparison with greedy, what we notice is that both TACO and SAS being much slower than greedy might be good to be, basically hot started with greedy. But the nice thing is that the completion time remains reasonable. So it remains in the order of minutes. These are all centralized algorithms that can be used essentially to plan. And one of the things that, for example, you could do with an algorithm like this one specifically, like ACO or SAS, could be that you could do speculative planning. So basically you could say, I have a plan right now, but if I want to consider conditions that change, so for example, some robots break or there's traffic that I didn't consider, I could, in the meantime, generate more plans. And, the probabilistic nature of these algorithms allows you to do that, because every time you rerun the algorithm, basically you find new plans. So these algorithms are particularly nice because they give you this possibility of planning on the side if you want. You can stop them anytime. You can stop them early if you want. So you find solutions early on if you want. But the point is, these are algorithms that are good, how to say, a good compromise between being super fast and being, very essentially optimal. One thing that I can show you is an algorithm run of the centralized, in this case, the centralized algorithm with just 2 robots, but in the case in which we show how we handle failures. So because I mentioned, right, failures. So in this case, we have 2 robots that look like rovers. There's a green robot, which is this one right here, and a blue robot, which is this one right here. So this robot is waiting now. The green robot is waiting for the blue one. And then when the blue one is close enough, we decide that the task is completed. In this scenario, we consider that, you know, sometimes failures can happen, and you would see a failure happening right now. The robots lost connection. And the thing is, the robots really lost connection in this case. It wasn't just something that we made happen, but just we don't know exactly what happened, but Wi-Fi just exploded in that moment for the two robots and they didn't talk. So the robot on the left, this one right here, the green robot, said, okay, I'm going to wait it out a little bit. Maybe the connections come back. But then the blue robot says, well, I waited long enough. Nobody's coming. I'm out of time. I'm going to do something else. So the task that initially had the blue skill fulfilled, now it has the blue skill back. In the meantime, the green robot arrives, but it doesn't find, you know, the blue friend. And so the robot, the green robot and the blue robot decide to go to the headquarter and talk about it. So hence the centralized nature of this. By the way, you notice that when they plan really hard. This is one of the things that these robots are doing, because navigation is actually really difficult in this environment. It's very dull. So we used SLAM here, and we had a lot of symmetries. And at some point we said, you know what, it's part of the failures we're going to consider, and that's okay. So anyway, the robots go to the headquarter, they replan, and then they find a new way to finish all of the tasks that they were doing. So in this case, we superimposed an extra layer of fault tolerance, basically, that allows us to replan quickly. And the replanning time that you saw is the real replanning time. So it was in the order of just a few seconds. Now, obviously, it's two robots, and you know, just a few tasks. So obviously we were not expecting long run times. But anyway, so this is just to show that we can handle failures gracefully. So one of the things we liked about our greedy algorithm was the fact that you know, it was so fast, but in no way it was the best possible idea. And so we have a paper that we are submitting right now on an entire design space of heuristics. And so here I don't want to go into much into details, but we broke the problem into three parts. One is selecting the task to be completed, and we have a number of alternatives, forming the coalition on the task, and then deleting superfluous robots. So we have a lot of things here, but in the, you know, in the style of trying to get to the other two lessons, I would just tell you there is this fun thing right here. And then we have a distributed formulation, which is essentially mimicking the three phases. So we have a task inclusion phase in which a robot picks a task and decides to add itself to that one. And then it keeps doing it until there is essentially a path for that robot that is selfishly built. And then the robots share their paths. And as they share their path, they might decide to modify their paths. And this can be done in two ways. It can be done either by updating certain variables about the times waiting at tasks that might be optimized, and that usually basically prompts the robots to create new paths. And there are some cases in which deadlocks might form, or the schedules are just unacceptable. And so in this case, we can detect these conditions. And if we cannot detect a successful solution in a reasonable time, we basically say that convergence failed, and we go back to basically starting over with the algorithm. So this is a very simple distributed way in which we can reproduce what we did in the centralized way. And one thing that is interesting is also that we allow the robots to abandon a certain task if the robot finds itself essentially not being unique. So if the skills offered by that robot are offered already by other robots. This allows us basically to lower the number of robots that are engaged in tasks, and also make them available for other tasks. What we found is that these distributed versions the algorithm is competitive with ACO. So basically, it's roughly in the middle between being optimal and being fast. And when we put everything together, this is again a comparison about all of the algorithms. This is a scatter plot in which the x-axis is the time of the fastest possible heuristic solution. So we want to be as left as possible. So we want to be as close as possible to the y-axis. And then this is the cost on the y-axis. So we want to be as flat as possible on the x-axis. So being in this corner, basically, it's nice. And what we find is that the heuristic algorithm obviously is super fast, but it's a little bit all over the place in terms of performance. And as we look at the other algorithm, so we have two versions of our distributed algorithm, and they are roughly in the middle. They are the ones that we are using right now, and we are boosting with machine learning and so on. So this is the stuff we're really looking into. We want to basically flatten out. We want to move this distribution here a little bit to the left and flatten it out a little bit against the x-axis. But essentially, the distributed algorithms fare essentially in the middle between being optimal but slow and very fast but also quite suboptimal. Okay. All right, so that was that. The point is of all this, it's actually really challenging to handle heterogeneity, and you need algorithms that are really well thought to do that. The second lesson that I would like to look into is heterogeneity as an emergent property. But before I do that, do you have any questions about what I just said?
So I have some questions that might be common to all the threads, but I'll start with one, with the lesson one, which is so this is very, very interesting and to some extent also intuitive. And I'm curious if you can relate it to the architecture, the specific architecture you chose here. Like, can you, for instance, can you say that choosing these decision-making architectures for your robots in some sense guarantees you to have this kind of result? I'm curious how much of this is thanks to the algorithm you design and how much of this is really the architecture of the problem.
So this is a very, very interesting question. I glossed over a gigantic amount of details here. So let me talk about a very interesting aspect about the problem itself, which is the interplay between the distribution of the skills among the robots and then the distribution of the skills among the tasks. Really just basically saying, imagine that you have robots that are super powerful and they have a lot of basically skills. So those robots are the robots that when they arrive, everything gets solved. Everybody wants those robots. As opposed to the case in which every robot is really, really specialized. So they have one or two skills, but that's a small subset of robots. A small subset of the tasks, of the skills that are needed. Even just these two variables playing together dramatically change the nature of the results that we see. Because essentially what happens here is that you are adding extra layers to the problem in terms of understanding that certain resources, for example, the robots that are particularly powerful, need to be scheduled more carefully than in the other case. So we are currently studying, especially these variants. And one of the things we honestly accepted is that machine learning seems to be the best way to do this. Because one of the things you want to do in that case is to try and discover patterns in the way the tasks that are presented to you require the robots. And then you want to say, certain robots that are special, particularly rare, those robots need to be treated specially. And so you need solutions that are based on that. I don't have yet, let's say, results that I can say, oh, this is awesome, it is a great intuition. It is literally the thing I'm studying next right now. And it's probably the most interesting thing that we discovered. Other than that, this problem is just interesting because the need to have a schedule that creates dependencies doesn't allow you to simply decouple the problem. For example, if you want to apply methods, I'm going to drop a random method, ADMM, so the alternate direct method of multipliers. Those methods are very, very good when you can decouple the problem and the dependencies are not too bad. We tried to actually attack this problem with ADMM. It didn't work out. We waited, we really tried for 6 months to do it. And then we just discovered you need to think differently. And then obviously you add to this the mutual, let's say, distribution of skills offered by the robots and required by the tasks. And already that complicates things horrendously. I didn't even talk about the spatial distribution because, again, in the order of, to minimize a little bit. So there's so many things about the architecture of the problem that can change, let's say, the nature of which algorithms wins over which other. And my guess, and it's really the thing I'm looking for now, is that these algorithms are the backbone. And my next step is to boost them with machine learning. So basically learn heuristics that rather than being algorithms that just take a picture of the problem and give you the answer. I'm not so interested in that, although it's possible that it's feasible. I'm more interested in boosting search algorithms. So basically take as an architecture our, for example, this one right here, this algorithm right here, or these algorithms right here, and find heuristics that are way more powerful, that can analyze the problem more deeply.
Yeah, yeah. I mean, that's for sure a very nice. Well, first of all, super interesting everything you said, but here there is a lot of potential, especially for warm starting this algorithm. I agree, that's a very interesting direction. Thanks so much for the long answer. Let's see, Ben has a question. Please go ahead.
Yeah, thank you. So my question is, in terms of the decentralized stuff that you've outlined, how would you say that your solutions here differ from existing? Because this kind of seems a little bit familiar in terms of like market-based methods, CBBA, other state-of-the-art things that kind of are the benchmarks today. How would you say that the stuff that you're offering here, I guess, differs?
Yeah, no, you're fully right. So the idea is that we are well aware of CBBA, also the PI algorithm. So in our case, and here I need to defer to my PhD student Akshay Aswale, who is the one that really worked on this. We are not doing exactly the same thing as CBBA. I have to remember exactly what the difference is. I'm thinking about it for a second. But we are not exchanging essentially the same kind of information. In our case, the information that we are exchanging is at the level of individual parts of a path, and CBBA doesn't do it in the same way. That's the thing I remember. But if you want, I can defer that specific difference to my PhD student, who would be able to let's say, to develop much more the answer on that.
Yeah, no worries. I was just, I guess my kind of where I was going with that was, have you, in terms of like the benchmarking compared to other algorithms, like, do you plan on, I guess, maybe using other existing decentralized methods for comparison rather than, I guess, and I agree that all the testing that you're doing in terms of solving the gap between like, just straight up greedy search versus like optimal MILP is like, that's kind of like, I don't know, I work in a bit of a similar space, and that's where I'm interested in as well. But I guess, yeah, that was my question is, do you plan on, I guess, do you know how this benchmarks relative to, some of those other decentralized methods that exist?
Yes, so I have a master thesis that is literally implementing the PI algorithm and CBBA now.
Oh, okay.
And so the entire point is that as soon as we have those ready, we're going to put them in the paper. So absolutely, that's the plan.
Okay, cool. Thanks.
All right, so this is it for the first lesson. The second lesson is that heterogeneity can be an emergent property, and we're going to study this with a completely different problem. It's the problem of collective transport. So this is a video that honestly went throughout the world. It was incredible. So many people showed it to me, across Europe and Asia and so on. They were like, you work on collective transport, you need to watch this video. This is an amazing video because it basically shows just how difficult it is to move a complex shaped object through an environment that, for example, has a gate opening. Let me already spoil the surprise. I'm not going to be able to show you a robot doing something quite like that, but that is the goal. Okay, we're working on that, and so you're going to see here our initial work and the baseline that we created, and the idea is then to exactly be able to do something like that. Now, what you learn from this video is that ants are just nothing short of amazing. They can do a lot of things, one of which is exactly being able to solve this kind of puzzles. So we essentially would like to perform collective transport with multiple robots. And when we looked at the literature, we found that related work had three fundamental assumptions: that either works that had predefined trajectories, or they knew the distribution of the robots around the object, or the robots had a comprehensive knowledge, essentially almost a map, if not straight out a map, of the position and dynamics of the payload and the robots and the obstacles of the environment. So the idea is there's collective transport when you look at it, it is based on a lot of assumptions that are not necessarily easy to realize in real life. And removing these assumptions is a big problem. One of the questions that we asked is, can we do that by applying multi-agent reinforcement learning? And so we just ventured into applying methods of reinforcement learning to the problem of collective transport. Why is this related to heterogeneity? You'll see in a minute, just in a minute. Let me just set up the problem. So the first thing we're going to do is we're not going to reinvent anything in reinforcement learning in itself in terms of algorithms. So we're going to take algorithms that have been studied really well, like DQN, DDQN, DDPG, and TD3. I don't go into details of how these things work, but the idea is we use this algorithm because this way we can compare apples to apples. Plus, there are other works that do multi-agent reinforcement learning and collective transport, and they use these algorithms as well, so we can compare directly to those algorithms. So we create, basically, as I said, we create our algorithm based on these things, and then we invented a very simple reward structure that we can reuse across all of these different algorithms, and then we made some code that you can actually play with. So the environment looks like this for us. We have a zone in which we can generate the object to transport, and then we can attach the robots in arbitrary ways that we want. Most of the things we're going to show in this presentation are circular objects, but I have also work done with irregularly shaped objects. And as I said, this is literally the next thing we're studying. So we have preliminary results on this that we're working on, and we hope to have a paper over the summer on that. Anyway, so the robots are placed here in a random place inside this area. And then there are obstacles in this area that can be either cylinders or a gate. And the gate can be wider or narrower. And in fact, as we train, we make the gate initially wide because, it's curriculum learning, basically. So we start with a very wide gate, and then we make the gate smaller and smaller and smaller. And then we have an area in which the robots need to drop the object. The area is initially very large, again, in the spirit of curriculum learning, and then it becomes narrower and narrower and narrower. So the robots need to learn to basically navigate and go to this location. So what the robots can do is essentially sense their vector to the object, not necessarily to the center of mass of the object. By the way, we do not assume that the robots know the center of mass of the object. They have a gripper that basically can sense the push and pull force of that a robot is exerting on the object. And then the robots obviously have wheels, and they can rotate their body with respect to the independently with respect to the point of attachment to the object. And so the robot can sense the vector to the goal, and this vector to the goal is sensed not necessarily in a perfect way. We add some noise to it. And then the robots can have an idea of where the object is. Again, the point C that we have here is just for simplicity the center, but it is not the center of mass. So this vector CG is an estimate that the robots might have, but it's not correct necessarily, geometrically not correct, with respect to where the object is, basically between where the object is and where the goal is. So this is what the robots know. And the reward that we consider is, in this case, calculated perfectly, the vector between the center of the object, the center of mass of the object, and the goal. And so the robots receive a reward that is related to the difference between this vector CG that is real with respect to the vector that they calculated, and in general the vector that they managed to actuate by moving around. So it's essentially a measure of coordination, because if you manage to go along the vector when it's necessary, you're doing a good job. And by the way, the robots have proximity sensors throughout their body, so they can sense the environment. But they do not have a map of the environment. They do not know where the obstacles are. They do not know, for example, the position of the cylinders when the cylinders are presented. They do not have an idea of where the gate is when the gate is presented. The very first thing we did, and we started really, really slow, was to have a network that took some sensor readings and was connected directly to an action network. Nothing fancy at all. And we prevented the robots from communicating at all. So the robots had to use their gripper and their force sensing to decide where to move. And this one was trained using a particularly well-respected method of training, which is centralized training, decentralized execution, in which basically the robots have all of their information available in a centralized way at training. But then when we execute, we just, in this case, let the robots execute their own local policy that is optimized by the training in a centralized way. All right, so this was just basically all vanilla, again, to create a baseline. And the real idea we wanted to propose was to have a system called global state prediction. So our idea was essentially to say that if we gave the robots a way to anticipate what would happen, okay, they would be able to probably coordinate better. And so we had a network dedicated to predicting what would happen. So we have our agents, and then each agent is basically talking to the other agents, and using that input, the agents are going to basically predict what will happen next. And we want to minimize the amount of information that is shared. So what we do in this case, again, in the spirit of minimizing the information shared, we take the proximity sensors, we average them out, and basically every robot sends a vector form of this averaged out proximity sensing information. So it's really not much what the robots share. And in order to do this, we had to modify a little bit centralized training, decentralized execution, and we modified it so that this aggregation of information could be offered to the robots. And so this method is, we call it aggregate centralized training, decentralized execution, because we have this extra element of aggregating information and then offering it to the robots. But then the execution is still executed in a decentralized way. So when we look at the performance between GSP and implicit communication, we see that across the board, all of the values of GSP are better than the values of IC. So essentially, GSP, we can say it offers benefits. It is a good idea, let's say, to add a component like GSP. And this is across the board in the different types of obstacles that we considered and configurations that we considered. So that's good. So that means that essentially the base idea of GSP works. The reason why we were particularly fascinated by GSP, we don't claim that it's, like a genius idea that nobody ever had, although it is different from existing methods. We can, if you want, talk about that a little bit more later. But the point that we found is that GSP generated task allocation. They generated specialization. It just fostered that. Because basically, we discovered it because we basically took GSP and we gave GSP a certain, sinusoidal signal. And we found that depending on where the robots were located across the object, the response of GSP was different. And so when I'm going to show you a video, you will see that the robots at the beginning do a funny little rotation at the beginning. And that funny little rotation is exactly the way the robots are using GSP to decide who's in front, who's in the back, and who is on the sides. And so what's interesting is that we didn't want necessarily to have a system to have specialization, but the act of predicting automatically generated this kind of thing for us. And that was interesting because very often, it's something that you want and maybe you have to design for. In this case, it's something that came for free just by the act of doing a very, very simple aggregate prediction. The next thing we did is like, okay, fine, all the robots are talking to each other. Can we avoid using a full topology and just having a ring topology in which, a robot talks to only a couple of friends around the object, around the perimeter of the object. And so we essentially now aggregate over only the neighbors. So this is the main difference that we have. And what we find is that the performance is essentially almost the same in certain cases. It's better to be obviously fully connected because you share more information. But in many situations, the performance is not negatively affected by limiting to neighbors, which is a nice thing to notice, because that allows you to actually do something, for example, like this. You can train for 4 agents, and then you can decide to go for example, for a larger system. So you can say, I train for 4 agents, but then I execute for 8. Or the opposite, you could have that you start with 8, but then you run with 4. Because you have this limited ring topology, this kind of scalability, comes as a byproduct of this. And one thing I can show you is just a quick demo of the robots doing their thing. So they just basically go around. They don't know where the objects are. They negotiate going around these obstacles, and then they eventually go in the right place, which is this place right here. One thing that was interesting to us is that we got failures, lots of failures. And in particular, these robots had a problem here. One of the grippers failed. And so the other 3 robots were able to, with the neighbor's version of it, were able to ignore the fact that one of the robots was lost and adapt to the fact that only 3 robots were left, which is nice. Again, it's one of the properties of just talking to your friends that are immediately, left and right of you, as opposed to having to talk to everybody and not receiving certain messages that you're expecting to receive. All right, so that was just a quick idea of like how prediction can generate specialization, which is something that definitely we were not expecting to see, not in this form. And we are deepening now our understanding of this system. In particular, we are adding memory, and what we want to do is to basically present the robots with more complex environments and see if the robots can do navigation in more complex environments using essentially memory. So we could, for example, have robots that, if they don't know where they're going, they can build representations that are map-like, so they can, as they perform transport, they can also navigate a complex environment. So this is the next big step. And these, again, are the baselines that we used to get there. That was the big thing. The other idea, obviously, is to have more complex objects. That's also another big thing. I guess the next PhD student, if I manage to get the funding for that, would be exactly working on these 2 problems. All right. So the last thing I wanted to talk about, and I'm a little over time, so I'll go quick on this, is that heterogeneity can be unavoidable. So heterogeneity being unavoidable can be, for example, seen as an example of spirit and opportunity being sent to Mars in 2 different places and failing in different things. But you don't need robots to understand that identical things can fail differently. For example, if you have 2 socks, it's always 1 sock that gets the toe, to create to poke a hole. It's never 2. At least that's what happens to me. Anyway, so we studied degradation over time, and we started with a very simple problem of collective perception, in which we have an environment with black and white tiles, and robots that need to decide whether there are more black tiles or fewer black tiles. So basically the ratio of fill of the environment, and they need to do it in a distributed way. Now, the twist is that this problem has been studied extensively, but the twist is that the robots are severely degraded. So basically, they have a binary sensor that can tell you whether the environment is black or white, but that sensor is severely impaired. So we're not talking about 10% noise, but we're talking about, for example, 52, 55, 57% noise. So basically, it's almost a coin toss. And the very first thing we did was to just devise a very basic algorithm that was essentially a Kalman filter that was distributed and had minimal requirements. So constant memory usage, constant computation, and bandwidth. So something very, very simple. And it worked this way in 3 parts. So the robots calculate a local estimate that is, imperfect, and then they collect the estimates of other people, and they calculate with that a social estimates. And then they combine the social estimate with the local estimate to form an informed estimate. And the way they weigh the individual contribution is using Fisher information, which is related to the variance of the estimate, basically. So something very, very simple, basically to create the baseline. And what we found is that this method actually worked really, really well. So as we look at the sensor inaccuracy, this is the black one is the one we are interested in because it's the one in which all of the robots are broken in a different way. And the black one is here in this case and here in this case. In an environment in which the fill ratio is very close to 50%, the robots can, in basically most of the configurations, even if all of them are broken, they can basically find they have a very low error, basically. And it's only in the cases in which your sensor is severely compromised, like, for example, the purple and the blue cases in which you have 52%, 57%, that you have an increased error. And this is for ambiguous environments in which you basically have 55% fill ratio. So this algorithm, despite being very simple, it's incredibly difficult to defeat, essentially. It worked really well just as a baseline. So the question is, like, what if the sensors degraded over time and we didn't know how they degraded? One of the things that we have basically as an assumption in our filter is the fact that we know how bad the sensor is, and so we can put it basically in the Kalman filter as a correction term. But what if we don't have the ability to know how bad our sensor is? So we cannot compensate for it. Then the idea is that we have expanded on that algorithm, and we're saying we're going to compute using the Kalman filter with essentially a putative B that we don't know. A putative B is our estimate of how bad our sensor is. We use a value that we assume is good enough, let's say. So we start with an estimate of it. And we communicate over that. But then what we do is that once we have applied the algorithm, the Kalman filter that we just saw, we use the value of the fill ratio that we have estimated to then estimate back the B. And so we basically do a sort of two-step procedure. In the first procedure, we keep B fixed and we try to guess a good F, and then we have all of the robots. The F is the fill ratio, so we have all of the robots estimate the fill ratio, and then the robots share the fill ratios to try and say how bad they are with respect to their friends. And so this way they can readjust their own calibration and basically readjust their sensors. One of the things that we noticed in this is that if we just update in an indiscriminate way, we can mislead the robots even if the calibration is correct. Because neighbors with flawed calibration shared inaccurate estimates. So we cannot allow basically this fourth step right here, the one that compensates for calibration. We cannot allow it to happen all the time. And then we should understand just when can I trust my neighbors. So we solved both problems with an hypothesis test. So basically we used ideas from hypothesis testing to say, first of all, do I trust myself? And if I do trust myself, I do not execute the fourth step. But if I don't trust myself, then I do execute the fourth step. And then when I do execute the fourth step, who do I listen to? I use the same hypothesis test to basically filter my friends and only take the people that I trust the most. And across the board, what we see is that activating the filter works much, much better than not activating the filter. So when we have degradation that is severe and it's distributed across the robots, and the robots do not know what this calibration is, then this filter actually, is better than basically not running it. It actually benefits. What we're doing right now is we are considering the case in which this degradation is dynamic. So basically, it's not a value that we have to estimate as a constant, but there's actually a trend, a downwards trend in the accuracy of the sensor. And so we're trying to basically expand this this filter to compensate for this gradual degradation. And that's that. If you give me 2 minutes, I am basically done.
Sure.
I can just talk about heterogeneity as an opportunity, and then if you have questions, I can stay a little longer. Otherwise, sorry, I'm a little over time. So heterogeneity is an opportunity. So I said a lot of things that can essentially say you can't avoid to be heterogeneous. Heterogeneous is a challenge. It is difficult. Sometimes heterogeneity just comes out of the robots interacting. here I wanted to just talk about an idea that just shows that heterogeneity can be an opportunity, for example, in construction. So here the idea that we had, and this was a few years ago, and I've been doing this with undergrad students. So all of this that you're seeing is done with undergrad students for fun. We have this idea of distributing construction using material, in this case, construction material here, that is intelligent. This basically acts as if it was active matter. And so we can have a symbiotic relationship between this builder that we decided are what's the name, inchworm robots, and the construction, but they're dumb, so they don't know what they're building. They know how to navigate the structure, but they don't know where they're going. And then the blocks, the individual blocks. And the blocks are essentially active matter. So they are a set of robots themselves to an extent that can talk and that can guide the actions of the inchworms, essentially. So the idea in this case is that we have a system that could be used either to just build a structure. Okay, fine. We can actually have a structure built of smart blocks. It seems kind of a waste, but you could in principle. The thing we're thinking about is more using this kind of material as scaffolding, that you can build at first as a way to then actually build the things that you want to build, and then you dismantle the scaffolding and build it somewhere else. And one of the ideas we had in mind was to do this in orbit or to do this in a faraway planet. And so this could be used to, for example, depending on the season, reconfigure habitats for future human settlements on Mars, or anyway, in general, ideas of this kind. So this was an early video that we made. This was done in 2021. We have an algorithm that basically allows us to coordinate any number of robots. Here you don't see the robot, it's a circle, just because my students didn't bother to animate in gazebo the robots going around. But you can see in some cases the animation worked, in other cases it didn't. But the algorithm does work. It was really just a gazebo issue. But anyway, so you can see that the algorithm is able to have multiple robots, basically divide the construction in regions, and then every robot builds a part of the region. And it can do this without deadlocks, and it can do this, with particularly large structures. So we have a recent video of the inchworm actually doing this, and the work of the students of this year is to do this with 2 inchworms and actually have a complex structures built with two inchworms. Again, so this is something that I'm doing with undergrad students here at WPI. So it's just, honestly, I do it for fun, and it's been a ton of fun to do. We have a couple of publications on it, but it's really just things I do for fun. So that's that. So conclusions, we have that heterogeneity can be a challenge, can be an emergent property, and can also be unavoidable, but it's also an opportunity. And so heterogeneity is something that, at least in my opinion, but in the opinion of I think most people that work in swarms, it is something that we will have to confront and manage over time. And it's probably one of the most exciting problems in general that we have in swarms today. And there's so much to do. So if you want to look for cool problems, definitely heterogeneity is one of those. These are the people that worked on all of these papers that we published and all the work that you have seen. And with this, thank you so much. Sorry for being a little bit over time. If you have any questions, I'm happy to stay. Otherwise, thank you so much.
Thank you so much, Carlo, and this talk is super interesting. And Jared has to leave early for a faculty meeting, and he let me to say sorry to you. And I have several questions about this. So the first question is about the stability. So, for example, for this kind of problems of moving robots, like using optimization or learning-based method, and it seems that the computation efficiency of different methods can be very different. So what is the general stability of the methods that you developed?
So what is the definition of stability you're using?
Sorry, I said scalability. I mean, how many robots can be? Yes.
All right. So you are talking about, for example, this part, the collective.
Yes. Let's say for example, this part. Yeah. How many robots can we use?
Yeah. So in our simulations, we went up to 16 and they worked. I don't have 16 robots like this in my lab. I think I built. We have 8 working ones here, and we have videos with 4. With 4, it works well. In simulation, we went up to 16 and it works. I know we have simulation with 64. Now, at that point, with simulations with 64, there's interesting things happening because the individual contribution of the robots becomes tricky because the object, it's a question at that point, the mass of the object plays an important role in the individual contribution of the robots. And that's a beast of its own that we really didn't look into yet, which is basically, you know, this idea of like having robots that are so small in contribution with respect to the big object that they have to do. That really changes fundamentally the nature of the problem. And so that is an interesting direction to look at because the way you handle that is much more delicate. I think in that case, you will need to expand the methods that we use. I don't think they're just going to work, basically, unless they work in ideal conditions, super ideal conditions. But one of the issues you might have, for example, is that if the shape of the object is not regular and the distribution of mass of the object is not regular, as the contribution of the individual robots becomes smaller and smaller, the way you distribute the robots dominates the dynamics of whatever you can do. And so that's where the scalability becomes a problem because, you know, the nature of the object and the nature of the attachment become the dominating variable there. It's something we haven't looked into. We are aware of it. But as you can see, we're building, you know, baby steps. We're building things step by step, starting from simple things. We are aware of that problem. It is not something we have looked into just yet. I don't have the space, the physical space to to just run real robot experiments that are so big. But it's a very, very good point.
Yeah, thank you for the explanation. Yeah, and interestingly, I have also worked on like similar like the collective transportation projects before, and it seems that like the how to deal with some like weird shaped project like a weird shaped object and how to calculate the distribution of the robot is a very tricky problem. Like especially when we try to like transport something like have the T shape like in the very early demonstration that you showed. Yes, and those problems are very interesting and yes. Another question from my side is like, how do you think about oh, wait, there's a question in the chat. Maybe I can read that first. So have you observed any dynamic behavior, for example, where, for example, utilization will start fluctuating?
What do you mean by utilization? Again, is it in this collective transport?
Yeah, I'm sorry, just, I guess this would be to ask you. Well, I mean, if you have a swarm of robots, then probably you can have, you know, you have different tasks assigned to you, right? I mean, just kind of in a stream. And then eventually you may start seeing, let's say you got a lot of, you have a task, I mean, stream of tasks. And then at times you may see like all robots utilized, and then you have times where just fewer robots because you have some constraints, you know, you cannot allocate some robots, I mean, just delay it. And then again, I mean, just once you get a little bit constrained, just a little bit eased up, again, just to get full utilization and just goes like in waves. The reason I'm coming is because I worked for Amazon Robotics, and I've seen a lot of these problems where, you know, depending on the order, stream, especially around holidays times. I mean, you can see like the system get really slammed and then kind of start fluctuating because, well, we didn't have this algorithm very perfect. So I was kind of curious, I mean, if you observed something like this, and if you did, I mean, how did you deal with this?
So I don't think we observed this specific problem that you were mentioning, but I think I will talk to my student. We never discussed, at least my student and I, about these problems of fluctuations. Or at least the fluctuations that we saw, we didn't attribute to the same phenomenon that you are describing. So I wouldn't be able to comment on that meaningfully. But if you want, I can give you the contact of the student, Joshua Bloom, who is working on this, and he might be able to answer you. It's a very interesting observation. I haven't come across that.
Yeah, thank you.
Thank you.
Thank you for the question and answer. And consider the time, I think we can end here. And from today's talk, I really learned that those kind of heterogeneity can really play a very important role for the collective behavior of the robot system, and can be a maybe key tool to enable the robot system to do more things and become more general. It's super interesting. Thank you very much for the talk, Carlo.
Thank you for the invitation. It was really fun, and thank you for the questions.
Thank you. Bye.
Bye-bye. Have a good one.